So there is another video that I have that sort of talks about the things that we can either put into or siphon off of the citric acid cycle. I want to take just a little bit of a deeper dive and talk about specifically amino acid sort of derived branch point metabolites. So an opportunity here to review some things, right? Pyruvate is one of those really important branch point metabolites. So let's use this as an opportunity to review now 5 things that we know that we can do with pyruvate. 3 of them are already written here. We can take pyruvate and make it into oxaloacetate using pyruvate carboxylase. Remember, that's only found in the mitochondrion. We can take pyruvate and we can decarboxylate that alpha keto acid using the pyruvate dehydrogenase multi-enzyme complex. Video out there on that if you need a sort of a reminder of the chemistry that happens with E1, E2, E3, all of that. We also have, and not written on here, but we have the ability to take and do some redox chemistry, converting pyruvate to lactate. Lactate being one of those dead end metabolites. That's lactate dehydrogenase that can do that chemistry. Another chemistry that we learned about, but not chemistry that we can do, is pyruvate decarboxylase. Pyruvate decarboxylase. And that, again, is under alcoholic fermentation. The products of that step, we don't get ethanol yet, but we're going to do carbon dioxide being eliminated from pyruvate. So it's an alpha keto acid decarboxylation chemistry, but we generate acetaldehyde. Okay, so that's 4 so far: pyruvate carboxylase, pyruvate dehydrogenase, lactate dehydrogenase, pyruvate decarboxylase, and finally, we're going to have transamination chemistry. So this is kind of the focus of what I'm going to talk about here. We can have alanine transaminase chemistry. So we're going to have this enzyme being called AAT. Is a way of basically taking pyruvate, which is the alpha keto acid skeleton of alanine, and sort of swapping. So I'm going to zoom in up here so we can sort of see these pieces here. So when we talk about AAT chemistry, so I'm going to highlight here, AAT chemistry is what we're seeing right up here. Okay, so what we're going to see here, and this is, the net is, there's a lot more involved chemistry than it's just a swap. Remember when we talked about disulfide exchange reactions, where you have somebody who's disulfide linked, and then you have somebody in a thiol form, so oxidized and reduced forms, and they just get to swap who's oxidized and who's reduced. We call that a disulfide exchange reaction. I sort of want you to think about this as an exchange reaction with, you either get to have your alpha carbon as a carbonyl, or you get to have your alpha carbon connected to a nitrogen atom. Okay, so we're sort of swapping out here what your alpha carbon looks like. See if this makes sense to you when we're looking at oxaloacetate. Oxaloacetate is an alpha keto acid, right? We've got an acid group here, and at the alpha position, we've got a keto group. Okay, so we've got oxaloacetate here. So highlighting, we've got oxaloacetate, and when we swap out that carbonyl, that alpha carbon as a carbonyl, with that alpha carbon connected to a primary amine, that generates aspartate. So some of the terminology that we want to get used to is saying oxaloacetate is the alpha keto acid of aspartate or aspartic acid. Similarly, if we look at this pairing, right, we can see alanine and pyruvate. So alanine, again, being the amino acid, so it has its alpha carbon, right? We call these alpha amino acids, right? That alpha carbon is connected to the amine group, or we've converted it into a carbonyl. So these guys are related. We can say that pyruvate is the alpha keto acid of alanine. So pyruvate, again, being an alpha keto acid. So it's really a amino acid exchange reaction, if you will. You have an amino acid and an alpha keto acid skeleton, okay? And then you swap them, and the guy who was the alpha keto acid becomes the amino acid, the guy who was the amino acid becomes the alpha keto acid. So it's this exchange reaction. This is going to be a key piece in our understanding of how we metabolize amino acids. So introducing it now, because it is an option that we can see for chemistry that can happen with pyruvate. Pyruvate can be converted into alanine, okay? So that is one way that we can sort of do this exchange type reaction with amino acids and their alpha keto acid skeletons. The other piece I kind of want to put on here, and just highlighting another way that this can happen, okay, is through what we call reductive amination. So reductive amination. So the net is sort of the same of what we do. We basically have, and here's another pairing, we've got alpha ketoglutarate is the alpha keto acid skeleton of glutamic acid or glutamate. Okay, so highlighting here, choose a different color. Alpha ketoglutarate and glutamate are sort of paired and matched together because alpha ketoglutarate is the alpha keto acid of glutamate. So writing that down here, alpha ketoglutarate is the alpha keto acid, and then we've got our amino acid. So we want to be able to see these relationships, right? Because if we do either, these amino acid exchange reactions, that's not what they're called, but the net is what you can think of it as. But if we're interconverting amino acids and their alpha keto acid skeletons, we want to say, who do you look like? Are you a citric acid cycle intermediate? Is there some way that I can feed you into a metabolic pathway that we know about? And that's what we can see here. Note too that these reactions are reversible. So again, we can go back and forth between these different pieces, okay? But we're going to see some really important, and we actually have highlighted where they are right now. So here's, again, alpha ketoglutarate. Here is oxaloacetate, right? And then here is pyruvate. So we can see these different alpha keto acids and their component amino acids, so we can sort of understand how amino acid metabolism is going to feed into this system that we've already learned about.